Okay, so here I've coded up our transition matrix exactly as we had talked about here. Is everyone okay with the way I came up with all of these numbers for the transition matrix? I just want to make sure we're okay that we came up with these things. Okay, and so here I can create the matrix right here, and the way I've inputted this into R, we would enter this by row, and when I do this, there it is. Okay, here's our transition matrix, up to however many decimal places we have. Okay, and just to kind of say, like, let's say the politician started at island 1. What we can do is we can multiply W times R. So currently, the probability of the politician is that there's 100% probability he's at island 4, right? If I multiply that vector by the transition matrix, then on the next turn, he has a probability of 0.5 of being on island 5, a probability of 0.125 of being still at island 4, and a probability of 0.375 of being at island 3. Okay. If we say, let's apply the transition matrix here, okay, basically we would apply the transition probabilities from island 3 to the other ones, the transition probabilities of island 4 to the other ones, and the transition probabilities of island 5, okay? And so what we see is that, okay, if he has after one iteration, he has a 0.5 probability of being at island 5. Now he has a 0.25 probability of being at island 6 after two states, because that means he had to flip the coin that proposed going to the right, and then he had to flip the coin that proposed going to the right again, and then he would end up at island 6. Okay, there's now a pretty high chance of being back at island 4, which is basically in state 2 he was at island 3, and at state high probability of being at island 3 and high probability of being at island 5. Basically, this is the sum of the probabilities of going from island 5 back to island 4 and the sum of the probability of going from island 3 back to island 4. Okay, so we have a pretty high probability there, and then, some lower probabilities. So this is after two transitions, okay? And then if we continue, this is after 3 transitions. We see this is kind of getting more spread out, but let me just, can I just plot W3? No. Bar chart? Bar plot? Will this work? Okay, so here, so bar plot, so this is our first day. The next day, we have the probabilities of being on the islands. The 7 islands is kind of like that. After that, it reworks this way, and then after 3 transitions, it's now this. Okay, and then I can continue on, and we can just see, all right, well, what does after 4 transition, what does this look like? After the 5th transition, what does this look like? Okay, and after 6 transitions, what does this look like? This is kind of what we have, all right? And then let me just kind of do let's see. I'll do 15 here. Okay, so we can kind of see. So this is reversing the time here, but we go from here and then we keep going, And we can see that after several iterations, this is after about 15 iterations, what do we see? The transition matrix, or not the transition, where we're located resembles kind of the distribution of the islands, right? Because the islands, if I create a vector of the island populations, which is just vector 1 through 7, and I create a bar plot of our populations, this is what the bar plot of the entire populations. After 15 iterations, our probability of being at each island resembles very much the target distribution, okay? And because at this point, this would mean that probabilities of transitioning away from each state is equal to the probabilities of moving back into that state, okay? We can calculate the eigenvalue of the transition matrix. Here we're doing eigenvalue of the transpose of the transition matrix, because the way R calculates the eigenvectors, vector is the same as kind of the standard notation, which is an eigenvector of a matrix A is such that A times V is equal to a constant lambda V, and in this case our eigenvalue being 1. But the way we have written our transition matrix being applied is that it is the vector W times the matrix T. So it's actually, it would be V times A is equal to V. So because of we've changed it from A times V to V times A, we're doing the eigenvector of the transpose. Okay, so here I get the eigenvector of the transpose, and this is what we see. These are the eigenvalues. So our first eigenvalue, which has an eigenvalue of 1, this is the eigenvector right here, this first column. So let me just, if we do the eigenvector, this is what we have. And it's hard to see this, but if I kind of scale this, this is the exact distribution of this. And if I were to multiply this instead by not 28. If I just take the first value, we can see they're proportional to the values 1, 2, 3, 4, 5, 6, 7. Okay, so if I just take the eigenvector, the first eigenvector, okay, and I divide everything by this value so that this thing becomes 1, which is then we can see that indeed the eigenvector is proportional to our target distribution of 1, 2, 3, 4, 5, 6, 7. Okay. Okay, so so that's just kind of an example of here is we set up the transition matrix according to this, and when we look at the eigenvector of the transpose of this transition matrix, we get the stationary distribution that we are targeting. Okay, so if this is T, then eigen of T transpose would be equal to our stationary distribution. Stationary distribution, which is equal to our target distribution. Okay, so kind of in so I guess the algorithm for the island visiting is 1, propose left or right via coin flip with probability equal to 0.5, and then basically compare, instead of talking about population, if we think of it as kind of the relative probability of each island, we would do compare probability of proposed versus current, and we would say probability of moving is going to equal to the minimum of proposed of the the probability of the proposed location divided by the probability of the current location, that versus 1. Okay, so this takes care of the possibility that if the proposed has a higher probability or higher population than our current one, this value is going to be greater than 1. So we just say that your probability of moving is 1. Okay, we take the smaller. Okay, and then if this thing is smaller, then we'll take this value versus 1. Right. So obviously if okay. It doesn't always have to be a coin flip. Okay. The only thing that's required is that for the metropolis algorithm is that our proposal needs to be symmetric. Okay. So symmetric means that the probability of proposing state A, or if you're at state A, the probability of proposing state B is equal to the probability of proposing state A if you're at state B. So the probability of proposing one way or the other is equal. So that's the requirement for the metropolis algorithm. So have to use a coin flip for proposals. Okay, the only requirement is that the proposal distribution symmetric, which means the probability of proposing A given we are at state B is equal to the probability of proposing B given we are at state A. And again, you know, we have our kind of our distribution W multiplied by the transition matrix T, and this equals W when W equals our stationary distribution. Okay, so W being the current distribution, after you've applied the transition matrix to W, and if you get back W, then you are at your stationary distribution, and with the Metropolis algorithm, the stationary distribution of the transition matrix is our target distribution. Okay, this was the Metropolis algorithm for the discrete case. Okay, discrete because we had defined states. We might have, yes?
What's the use of this, practical use, or like where you see this come up for the Metropolis algorithm?
Yeah, just trying to figure out the some target distribution, target probability distribution that we cannot compute directly. So like in, so the example I had at the very beginning of today was that we might have some kind of distribution according to Bayesian statistics, and because of this thing in the denominator, this target distribution could be very difficult to compute directly. Okay, if we're able to get calculations of just the numerator part, okay, so if we're able to just calculate this, then we can use the Metropolis algorithm. Okay, and so what I've shown you would only work in the discrete case, but yeah, a lot of times you'll have some kind of distribution that we can't do, we can't get directly. Just the integrals get too crazy, or just the math breaks down. So this is useful in those situations. Okay, this was for the discrete case. A lot of times we are dealing with a continuous case. So how do we do this? Okay, well, it's very similar. Okay, so we'll do Metropolis algorithm for the continuous case. So again, here we're trying to figure out, this is the target distribution, and maybe this is unknown to us, or maybe we only know it up to some proportionality constant, okay? And we want to draw samples from this thing to get an idea of the shape of our target distribution, okay? So we want to get an idea of this distribution, even though it is too complex to get directly. Okay, and so what we do is we have rather than a proposal coin flip, we have a continuous proposal distribution, okay? So for the continuous case, okay, rather than coin flip to propose the next value, we use a proposal distribution. Okay, a common choice is the normal distribution centered at theta current. Okay, so we will just say, theta proposed is selected randomly from a normal distribution centered at theta current and some arbitrarily chosen standard deviation value for this thing. Okay, and so if you are currently here, this is your theta current, and get something like this, and maybe you propose a value right here. This is going to be theta proposed. Okay, and so you propose a new value, and then the Metropolis algorithm works exactly the way it did before. And we say, we might, with the proposed value, now we have a choice. We're either gonna stay at my current value, or I will go to the proposed value. Okay, so with once you propose a value, once the value is proposed, we can either remain or move. Okay, and so the probability of moving is going to equal the minimum between, what do you think? The probability of theta proposed divided by the probability of theta current and 1. So if the probability of the proposed value is greater than the probability of the current value, we're definitely going to go. And if it's not, then we might go, and we use this ratio to decide whether or not we go. Okay, how does something like this work? Maybe I will illustrate this with an example here. Okay, so here we're going to say our target distribution is going to be the sine function, but only between 0 and 3. Okay, so it's going to, the target distribution, okay, is proportional to sine of theta plus 2 for 0 less than or equal to theta less than or equal to 3. Okay, so what does this thing look like? Okay, so from 0 to 3. So if we, here is the line 2. Okay, and so at basically we go pi, and so it goes up, and it goes up. Does it just only go up? Does it go down? Yeah, no, it goes, sorry. It goes up, and then it goes down, and then it only goes down, and it doesn't go down all the way, right? Something. Okay. Now I'm embarrassed. I just double check. All right, so we'll just x will be sequence from 0 to 3 by equal to 0.01, and then y will be sine of x, and then we'll plot x, y, type equals L. Oops, and then y sine of x plus 2. Okay, so this is okay, so this is kind of what we have. Oh, I'm sorry. Not from 0 to 3. 0 to 3 pi. Oh, okay, sorry. 0 to 3 pi. That makes a big difference. Something happened. Okay, so if I go to 3 pi, sorry, I forgot the example that I was using earlier. So at 3 pi, we've done, we can go up, we're going to go down, and we're going to go up. We'll go up, down, up, and down, right? This is what we have. So this goes from 1 to 3. Okay, so that... 3 times pi. Y is this, and we'll plot this. Okay, so this is going to be our the density that we want. Okay, so I don't know how we can draw some sample from this, right? Okay, so we want to be able to approximate this thing, but how? Okay, well, and we have no idea what the normalizing constant is. I mean, we could do the math, and we could figure out the normalizing constant so that this whole thing has an area of 1. But we don't have to. That's the beauty of this, okay? So we just start at some random location, okay? So I guess I'll start at location 2. That's just an arbitrarily chosen place. And then what I'm going to do is I'm going to use a normal distribution. I'm going to draw one value, and our norm, we're going to use the current value as the mean, and then j will be the size of my standard deviation. Okay, and the screen got cut off. Sorry. And so here I'm running a loop so that we can see the effects of choosing different standard deviations for my proposal. Okay, so here I'm going to start off 3 pi, start off at like location 2 here. Okay, and at location 2, should the next value I propose be something like 2.1 or 1.9, that's one possibility. If I use a small j being the standard deviation of the normal distribution that I used to propose, then I could have, with small j, my next proposed value could be something like 2.1 or 1.9, okay? With medium j, I might propose something like 3 or 1 if I'm currently at 2, okay? I can also have a huge j, right? With very large j, I can propose 23 or negative 17, okay? What would happen if I proposed 23? Because I'm at 3 pi, so that's like on the order of like 9.5 or something, right? If I proposed 23, what would happen? The next value I use would just be 2, right? Because if I say, okay, well, what's the probability of my proposed value the probability there is 0. The distribution doesn't exist at 23. The distribution doesn't exist at negative 17 either. So the probability that I'm going to go there is going to be 0. Okay? It's fine. The Metropolis algorithm is guaranteed to work if you let it run long enough. It just might take a really long time to give you the properties that you want. All right, so I've written some code here, and we're going to use different values of j. First, I'm going to use a j of 0.5, a j of 3, and a j of 20. Okay, and you can see I'm going to run 50,000 iterations of this, and what I do is I propose a new value centered at the current one with standard deviation j. I'm going to propose that. Okay, the ratio is going to be, I plug in the proposed value into my function f, and I plug in divide that by the current value in the function f. Okay, so this is what I have. And then I'm going to move between the minimum of 1 and the ratio. So here I'm just coding exactly what the algorithm says I need to do. Right? Okay, and then I'm going to draw a random value between 0 and 1. And if my random value is smaller than this move, then my proposed value will become my current value. I'm keeping a vector of accepted as 1. Okay, so my proposed value becomes my current value, right? And then I will say I accepted it. Okay, if my and whether or not this happens, for the next iteration, I'm going to just take my current value and store it as the next x value. Okay, so if I choose to move, then my proposed value becomes my current value. Otherwise, and I would store the new current value into my x. And if this move is not accepted, then I just take my current value and it goes into x again. Okay, so the same value will get repeated again, right? Which is okay, because we're just trying to get an approximation of the target distribution. Okay, so in we recognize that in true math you would not get the same value twice in a continuous distribution. When you're doing the Metropolis algorithm, there's a very you're going to get the same value show up multiple times. Okay, but that's okay because we're just trying to get an approximation. So we will store that. So if it's not accepted, the current value doesn't change, and the current value goes into my x vector there. And then here I'm going to print out the results here. Okay, so I will go ahead and just run this loop, and it's done. Oh wait. Forgot to store my function f. Okay, and here we go. Oops. Let's okay, so this is the picture of the Markov chain, just the first 500, okay? The true Markov chain ran 50,000 iterations, and I'm just showing the first 500. And what we see is that almost every single value that was proposed got accepted, okay? Because I'm using a very tiny j. I used a very small j, meaning the normal distribution that I used to propose the next value, it always proposed values very close to the current value. Like if I'm at 2, I would propose like 2.1 or 1.9 or something like that. Okay, I propose small changes, and so almost every single value I propose gets accepted. Okay, and so we see something that's very, very, very jagged. and this is the resulting distribution, okay? And we don't have, both peaks are not quite equal, because what ended up happening was, I ended up kind of hanging out in this region a little bit too much, because I just took tiny little steps, and I was going a little bit that way and a little bit this way and a little bit that way and a little bit this way, and I ended up hanging out in this region a little too much, even after 50,000 iterations. Okay, here is something with a little bit more of, you can see the kinds of values that I've proposed, and so you can see the jump from one iteration to the next. We have kind of larger steps, and we can see also little flat lines here. Okay, the flat areas mean I proposed a value and it didn't get accepted, and I proposed another value and it didn't get accepted, because we're kind of proposing things that are far enough away that maybe it won't get accepted. So we see little flat lines here. And then if we look at the resulting distribution of, this is our target, this thing, I think resembles our target distribution that we wanted, right? The sine of x. And of course, it's not perfectly smooth, but this gives us a pretty good idea of what the target distribution looks like. Okay, and then lastly, this is the case where I've used a very large proposal value. Okay, so if I'm currently at 2, or if I'm currently at 3, I might propose values like 23, I might propose values like -17. So a lot of times I'm going long stretches where I'm not accepting any of the values that I've proposed. Okay, so that's what we kind of see. We see a lot more flat values, the same value being reused over and over again. So that's what we see here. And the resulting histogram, we see doesn't, kind of, but it has some problems here. Okay, the Metropolis algorithm will work even if you have bad proposal values. It's just you've got to let the chain run even longer. Okay, is what happens. And so there's often a lot of tweaking, and there's tips and strategies on how you can pick proposal distributions and how to use optimize the properties of those proposal distributions so that the chain has what we call nice mixing properties, meaning you're going to get search the whole distribution in a kind of a timely manner. Okay, if there's like a choke point in the like if your if the target distribution has something like this, the Metropolis algorithm would have a hard time, because first it has to survive, because remember, it's just proposing, do I go that way or do I go this way? And it's got to survive going through here and getting over here and exploring this region, right? Given infinity time, it will do it, but in practical settings, we don't have infinity time, and so it might not work out. Okay, so this is what we have. Is this okay? So so again, yeah, we just propose some kind of thing. The normal distribution works well as a proposal distribution because it is symmetric. Meaning that if J is our kind of our jump distribution, the probability of kind of the proposed value given our current value is equal to getting our current value if we were at the proposed value. So if we have something like this, it's terrible. So if I'm currently here, theta current, the probability of proposing here is the same as being at theta proposed, and getting this height of theta proposed given theta current, this is equal to this height, theta current given theta proposed. So this is the same height. Okay, maybe not in my picture, but theoretically, in practice. Okay. If we can generalize this to something where if the proposal distribution is not symmetric, we can still use this thing, use the algorithm, except it becomes we have the Metropolis-Hastings algorithm. Okay, so the probability of getting the proposed value given your current value does not necessarily equal the probability of getting your current value given your proposed value. Okay, what do we do in a situation like this? Okay, well, the probability of moving, then the probability of moving is still going to be the minimum between some ratio and 1, okay? Except it's going to be the ratio between the probability of the proposed divided by the probability of the current. So this part's the same, but then we have to factor in the difference in these values here. So we say, you know what? One of these things was greater than the others, or is different. So we're going to say this is our adjustment factor. Okay, so this is kind of the same ratio as before, but now we have a kind of a adjustment factor for a non-symmetric proposal. Okay, and it's still going to be the smaller between this and 1. So if this entire quantity ends up being bigger than 1, you definitely move. And if that proposal quantity is less than 1, then we may or may not move. Okay, and if you don't move, you just reuse the same value again. Sorry, let me respond to this. Okay. Is this okay? Okay, so this is just for some non-symmetric proposal. So if it's not a normal distribution, it's like, I don't know, you use some other skewed distribution and you're centered somewhere else, and I don't know. Okay, then you get something like that. Okay. Let's see, I got about 25 minutes left. What should we do? Okay, I'll show you a kind of a neat application of the Metropolis Hastings algorithm rather than doing the Gibbs sampler. I can live with that. Okay, so I feel a tiny bit bad that we're not going to get to the Gibbs sampler, but I think we'll do this. Okay. All right. So here is an application of the Metropolis Hastings algorithm, or not the Metropolis. It's just going to be the Metropolis algorithm because it's going to have a symmetric proposal, and it's not even going to be for like finding some unknown. It kind of is, but it's not going to be like a Bayesian application of this. But I think it's kind of a nifty little, I think it's a neat application, all right? What we're going to try to do, so this is an application of Metropolis algorithm. Metropolis algorithm. Okay. We were going to just try to crack a cipher, okay? We'll try to decode a simple replacement cipher. Okay, so what I mean by a replacement cipher is that, you know, you have your alphabet, A, B, C, D, E, F, G, all the way to X, Y, Z. And a replacement cipher just says, you know what, every time we see the letter A, we're going to replace it with the letter, I don't know, K. When I see the letter B, it will become the letter D, and the letter C will become the letter M, and the letter D will become some letter, I don't know, O, and so on and so forth, okay? And you just shuffle, basically all of these letters have been shuffled around. Okay, so maybe J and T and P. Okay, just some. And so the word day becomes, in this case, O K T, right? According to the cipher that I've written. Okay, so how do we go from this? If we see this, can we get back the original? Okay, this is This is what we're going to try to do. And so the tricky part is we want to figure out technically the space of it's a little strange to think of this, but our probability space has 26 factorial possibilities, right? So every single possible rearrangement of letters is going to be in our space, a space of possible solutions here, okay? And what we want is we want to find the one out of those 26 factorial that corresponds to the true mapping. Right? So how can we even go about searching through all of these things? Well, so let me just write that down. Okay, there are 26 factorial possible mappings, and only one is correct. Okay, how can we find it? And what is just I want to know what order of magnitude is 26 factorial. Oh, I can't even do it, right? No, wait. Factorial 5 is 120. Okay, factorial 26. Okay, it's on the order of 10 to the 26th power. So that's on the order of 4 times 10 to the 26. Okay, so that's like, what's Avogadro's number? Something around there, right? Number of atoms in a mole. Okay, so there's a lot, right? Okay, what we will do is we are going to create a way to evaluate maybe the probability of some possible arrangement, okay? And the way we will say so we will have a way to evaluate the probability of some, it's not really the probability, it's just something that gives us an idea of the probability, some particular we'll say decoding pattern. All right, what is this going to do? Okay, what we will do is we will just look at letter-to-letter transitions. Okay, so we will look at letter-to-letter transitions. So basically, if we go Q to U, we'll have a high probability, and going from the letter B to the letter E or B to A, these will all have pretty high probabilities, higher. But going from B to J or B to, what's another thing that is not likely to follow B? X, or B to, I don't know. Yeah, I don't know, something, right? Okay, these will be low. All right, and how are we going to even do this? Well, so we will set up basically a 27, which will be for 26 letters plus space. 27 by 27, basically letter-to-letter transition matrix. This is I'm telling you what we're gonna do because I have the code already written for this. Okay, and so these letter-to-letter transition probabilities will come from like analyzing some large text. Okay, so I think I have the text of War and Peace, which is we're going to look at the English translation of the Russian War and Peace novel, which is known for being notoriously long, right? And so so we'll look at that and we'll establish some probabilities of letter-to-letter transitions. Okay, so we do this, and then now that we have this thing, we can calculate kind of a quote probability of our current cipher. So we might have X, T, J, K, V, S, P, P, Q, R, I don't know, and A, B, R. Okay. And then, so this is kind of our current text. All right. And then maybe we have a proposed text after applying some cipher. So the proposed text maybe does a simple transition, and instead of XTJ, it now becomes ATJKVS. So all the X's got changed to A's, and let's have something other than an A here. I don't know. Okay. All right. So between this thing and between this one and this one, just because we've switched the X to the A, this one suddenly looks a tiny bit more likely, right? This is a tiny bit more probable. Okay, and because it's more probable, we will accept this switch. Okay, and we will also accept less probable switches based on our metropolis rule. Okay, so so the switch will be accepted because it is more more probable. Okay, and less probable switches will also be accepted using the kind of the metropolis ratio, right? Metropolis algorithm ratio. Okay, and and I'm sorry, our proposals will just be, we will swap 2 letters in the alphabet at a time. 2 letters in the alphabet. Okay. Okay. And how does this work? So again, keep in mind the metropolis algorithm is supposed to give us something that resembles the total distribution of the thing. Now, we aren't, technically, we're just looking for the one thing that that decodes the thing. So how does this work? Well, according to our rule, we because of our probabilities based on the letter-to-letter transition matrix, we now have a, quote, probability distribution over all 26 factorial possible letter arrangements. Okay, so with our kind of letter-to-letter, probability matrix, we now have a probability distribution over all 26 factorial possible arrangements. okay, almost all of them, nearly all, will have probabilities close to 0. Okay, so nearly all of these will have probabilities close to 0. And then some will have very high probabilities, right? The one that is correct will probably have the highest probability. And then ones where certain letter swaps will be probably also very high. Like switching G for H will probably still result in a high probability because you can have words like have versus gave, and I don't know. Other words were similar, where switching an H and a G still looks kind of reasonable, or switching, maybe two vowels like an A and an E maybe will still end up being some kind of reasonably sounding something that looks still like English, okay, even if it's not full words, because there's no dictionary of words. It's just based on letter to letter transitions. So going from E to N probably has the same probability as going from A to N or something like that. Okay, and so we'll have probabilities near 0, and so the Metropolis algorithm will give us a distribution that resembles the actual probability distribution, which will naturally have, and this probability distribution will naturally have a high probability near the or at the correct kind of arrangement and other similar arrangements. Does that kind of make sense, what we're trying to do? Okay, so let's let me run this code. Where is it? That's not it. Let me clear out everything. Okay, so we're going to load up okay, so I'm loading up War and Peace, the text. Okay, and we're going to set up our transition matrix, and this is going to go through all the lines in War and Peace and set up our transition matrix accordingly. Okay, it's taking its time. All right, so it's going through, how many lines of the, is this? It's 3.2 megabytes of just plain text. So it's pretty big, I think. 66,000 lines. Oh, okay. So this is gonna, sorry, it's gonna take a little while. So we'll sit and I mean, if we want to just explore this code a little bit, it's basically gonna just, what it does is it takes a look. It goes through each line, and it just says, you know, subset kind of the thing to the current letter, and then compare it to the last letter. Okay, so it updates the last letter and the current letter, and at that intersection in the transition matrix, it's going to increase 1. So if the current letter is, if the last letter is a T and the current letter is an H, it's going to take the value that intersects T and H in the matrix and increment that by 1. And it's just going to do this for every single thing. Okay, so it's done now. Okay, and then and so if we look at this and I type out what transition probability.matrix is, this is what it looks like. Okay, so it just says, you know, from A to this, and these are all the things, and it's kind of hard to see, so we'll just we'll, I gotta load up ggplot. We'll plot this. Cannot find the function melt. Right, what am I forgetting to load? Library has melt. Reshape. Package reshape. Okay, so here, these are the ones with the highest probabilities. Okay, so we see Q to U has a very high probability. E shows up quite often after the letter V, and the letter H also after the letter B. Okay, from B, we're likely to go from A to E to I, or L, or O, also R, and also U. Okay, and sometimes Y. Okay, not very often other letters. Okay, from the letter X, we might go from X to the letter A, X to the letter C, X to the letter E, X to the letter I, X to the letter P, or X to the letter T, but not really other letters. Okay, so you know what letters, you know, N shows up often after I and things like that. Okay, and from the letter Q, we pretty much won't go to any other letter except for U. From the letter J, we will only go to like vowels, A, E. There's not a whole lot of J-I words, so A, E, O, or U, and things like that, okay? And then from the letter D, we're most likely to go to a space, okay, or something like that. And if we have the letter Y, we're very likely to go to a space. Okay, so that's what we have for the kind of the transition matrix for any of the letters to any of the other letters. This is we also write up some functions to kind of decode the letter. And then here is a way to calculate the log probabilities. Okay, so the log probability, rather than continuing to multiply tiny numbers together and get it possibly running into an underflow error, we're going to add log probabilities. Okay, and we can still try to explore the landscape of all the possible distributions, but now we're looking at the log probability. Okay, so this is what we have. Okay, and our correct text will be taken from Hamlet. Enter Hamlet, where Ham says, "To be or not to be, that is the question, whether 'tis nobler in the mind to suffer the slings and arrows of outrageous fortune, or to take arms against a sea of troubles, and by opposing end." Okay, and now we will code this up, and after we run it through the cipher, that thing where it says enter Hamlet Ham to be or not to be looks like this. Reversert something, right? Gibberish. Okay, and so what will we do? We will just propose a letter-to-letter swap. Okay, so here we're going to just start with an initial random mapping. Okay, so my mapping says A goes to Y, B goes to Z, C goes to E, you know, all the way through Y goes to Q and Z goes to M. This is my current mapping. And if I run it through our, so this is our current coded thing. If I try to decode it using my current mapping, so, you know, between this and this, which one seems like it's better? I don't know. I can't tell, right? I'm not. But what we will do is we will run it through the transition probability matrix, and that will give us that will assign us a current likelihood. Okay, so my current likelihood, log likelihood, is negative 1030, and then let's just try the proposal likelihood. Sorry, okay. And so at this point, so my current, okay, so these are, wait, my proposal mapping. Oh, okay, well, I'm sorry, I haven't proposed anything. So, this is what we do. And so, yeah, right now, we don't have a good thing. So our current likelihood is negative 1030, and let me just try this versus okay, so we're just getting something. I don't know why it's giving me the same number. Okay, but anyway, we're going to just run through iterations, and all we're going to do is we're just going to swap two letters. We're going to propose a mapping where I'm just selecting two letters at random, and then we're going to say, okay, you know what? We're going to put that letter, and we're going to move it over here, and that letter we're going to move over there, and then we will just run it through the thing and see if we should accept it. Okay, and so we will do this, and you can kind of see it go, and so it's saying, based on my things, it's starting to just, now we're getting things that look a little bit more and more like English. It's not really, it's not English, but at least it has the form of looking something like a real, like you might believe this was a foreign language that you are unfamiliar with, because at least it has like some vowels in the right places rather than just complete gibberish. It is still gibberish, and then at some point, you know, it will propose a transition that's like awesome, and maybe you know, we'll see it. So it's going, and again, it's just using this transition thing to decide. And so this is, it's running, and it's just, all it's doing is it proposes a new mapping, and look at that, we got the word, well, not quite, we're getting something, right? And it's just proposing one swap for another letter swap, and it just runs it through the probability matrix or the transition matrix to get kind of a probability score of what seems like a does this seem more likely or unlikely than what we used to have? Yes?
Why would it accept RNG when it went from ING in the third word?
Yeah, it's because the thing will still accept things that have lower probabilities. The Metropolis algorithm is not a greedy algorithm in that it forces only ones that improve. It accepts ones that go in the opposite direction, but it only accepts it with a lower probability. Okay, so yes, it can accept RNG versus ING because for whatever reason it said, I don't know, maybe it said it had a lower probability, but it said, the drop in probability, is something, and it flips, it picks a random number between 0 and 1, and then, and if that number is smaller, it will go. Maybe. I hope this works. How long is it gonna take?
Space is one of the letters.
So not for the mapping. Space is one of the letters in the transition matrix, and so that gets used in the calculations, but we're not going to try to map space to a letter. So space is not in a possible mapping here. So what is this? Enter Hamlet ham to be or not to be. That is the question, or that is the, so let's, I wonder if I messed something up here. Because it seems to be getting stuck. Let me stop this. I have a feeling I messed something up in here, but yeah. Let me just. Okay. Oh gosh. It's got to run through this whole thing again. Okay. Well, that's disappointing. I will post this code. I will make sure it runs and I will make sure it works, and I'll post the code so you can try it out on your own machine and see it work. But it is just kind of I don't know, just more like, it might be a little bit gimmicky, but it's a fun little application of the Metropolis algorithm in searching all the possible decoding things. Okay, I'll just let this run and we'll see what happens. But you don't feel like you got to stick around for this. Yeah.
I have two questions. One about the homework. There was a task 2.
Yeah, okay, so here it's running. I don't know, we'll see if this.
We get on this.
I don't know.
I
We'll see
can
if it works. Or something.
Yeah,
Just
the
like
gym one.
It worked earlier.
what was the gym one?
We were debating for the output of that, like that task. So you said it's
Yeah,
is it
like,
equally
like,
valid or
at
really
what
different?
point